We'll start with our next invited talk. So the title of the talk is NIST Standardization of Post-Quantum Cryptography and Beyond, Present Challenges and Future. The speaker is Dr. Angshuman Karmakar. He is an assistant professor at IIT Kanpur in the Department of Computer Science and Engineering. His research interest lies mostly on post-quantum cryptography and computation on encrypted data, which are currently shaping the landscape of cryptography and computer security. His work spans a wide spectrum of these fields, such as developing theoretical instruments for efficient scheme design, designing algorithms for efficient implementation, discovering side channel, fault, and microarchitectural attacks, and proposing countermeasures. Sir, welcome. So first, I will request Sri Dilip Kumar Burman, sir, Assistant Controller Office of CCA, to felicitate the speaker with a shawl.
Okay, hi. So thank you for the nice introduction. So today I'm going to talk about post-quantum cryptography, and probably you know that there is a new standardization has just happened 2 weeks back. The new fifth standards have come up, the NIST. But is it enough? So my talk will broadly cover all those things. And what next? What the next challenges lies in the world of post-quantum cryptography? So I'll not go into very deep technical details, but it's more of an overview. But yeah, feel free to ask me questions after this. So everyone, thank you once again. Good morning and welcome. So let's see. We know that asymmetric or public key cryptography is an indispensable and crucial component of security in our digital ecosystem. So they have lots of applications, from digital currency to digital signature, homomorphic encryption, secure key establishment, and many more. Now, the security depends on the hardness of some computational problems. So the majority of our public infrastructure is based on RSA and elliptic curve cryptography. So basically, their hardness is on integer factorization problem and the elliptic curve discrete logarithm problem. So as I said, our whole these two problems secures our entire spectrum of the digital ecosystem. Okay, so the problem is that given RSA, so you are given an N and you have to find PQ. Similarly, for discrete logarithm, we are given K and G, you have to find E. Now, these are actually very hard problems to solve. Now, even if we combine all the computers in the world, time to solve just one practical instance is much more than even the age of the universe. Okay, so this is a quantum computer, and this man is Peter Shor. So in 1994, he discovered an algorithm, which is a quantum algorithm, which can factorize a number n into its prime factors, and it runs in quantum polynomial time. Soon after this problem was discovered, there was another algorithm by John Proust and Christoph Zalkan, Proust-Zalka's algorithm, which can even solve this ACDLP problem. So basically, with these two problems, this is catastrophic for our current public key infrastructure. Okay, so as these two problems can break our current public key infrastructure, we need quantum hard problems to build our next generation of public key cryptography. Now, a very watershed or landmark event that happened in the world of public key cryptography is this NIST standardization for public key cryptographic schemes. So, a brief chronology. So, they first announced the plans for standardization in 2016. And on 22, after many rounds of 3-4 rounds of evaluation, they published 3 schemes which are going to be standardized. There's a Kyber, Dilithium, Falcon, and Sphinx. And in just 2 weeks back, they have everything published as a FIPS Federal Information Processing Standard. Now, we also designed one scheme, and this was actually one of the 4 finalist schemes. It's called Saber, which was one of the finalist schemes in this process. Okay, so NIST standardization is not only standardization. So there are many standardizations. So for Australia, EU, France, Japan, South Korea. South Korea is not even talking about NIST standards. So see, they are almost following the NIST standards, but South Korea is currently running their own standardization. It's called Korean PQC standardization. So this is the NIST standardization. So we have now PQC standards, and we ultimately go here, this widespread deployment. But to go there, we have to solve many more problems. So for example, we have to do efficient implementation on different platforms. The biggest threat is physical attack analysis and their countermeasures, masking, formal verification, and much more cryptography so that we have enough confidence to put them in the public domain, right? Okay, so I'll talk about very few challenges. So one biggest challenge is lightweight PQC. So this is a learning with errors problem. Probably, this is the most dominant or very popular scheme, hard problem to design post-quantum cryptography. So on the left-hand side, so the items in the red are the public values, and the green are the secret values. So these are basically kind of a system of approximate equations. The goal is that given A and B, you have to find either S or E. Both are equivalent. Now you can see that if E was not here, it is very easy to find. You just do some Gaussian elimination and it will give you S. But unfortunately for the, fortunately, unfortunately, whatever you say, that if you add E, this becomes very hard. And Rajab's original proposal actually described this, they proved it, that this is a quantum hard problem. So, but the problem here is, see, if we sample all of these things from randomly, we have to perform this matrix vector multiplication, which is of order of n square or n cube algorithm. These are extremely slow. These are extremely slow, and the sizes is quite large. So in 2012, but there is a very popular scheme based on these problems called Frodochem, which is in use in many products. Okay. So yeah, now we actually have come into module learning with errors. What do we do? And Kyber, dilithium are all based on these things. So here you see, earlier we were just sampling each number, but now we do not go for a matrix of numbers, but we matrix of polynomials. So each of them are generated are polynomials, and these are all ideal vectors. So here on the left, instead of this large A, we get a polynomial matrix. The secret is also a polynomial vector, error is also a polynomial vector, and the output is also a polynomial vector. Now, this is actually a trade-off between a standard and ring lattices. So ring lattice is also, it is very well known. New Hope, one is a very famous algorithm dependent on this. But the problem is that with that people do not are satisfied with the security reductions of ring learning with errors, because whole polynomial is generated by whole matrix is generated by one single polynomial. And people say there are lots of structures, it might be broken. There's a huge rift between the researchers whether it is at all secure or not. So there is a trade-off, this module learnings. So it is not fully ring, not fully standard, something in between. What is the advantage? Advantage is, see, since each of these polynomial multiplication, you can do it using very fast algorithms like NDT, which runs in order in log n, right? So it is, and also there are much more elements like standard lattices. So it is believed to be more secure. Actually, there are reductions which shows it much more secure, like standard lattices. So yeah, the thing is now here, if we consider there are L corps L polynomials here, right now there is no attack that can take advantage of these structures. So we assume that if L is this size of this matrix L cross L, and N is the size of these polynomials, if L cross N becomes some the rank of the standard lattices, all of their security is same. Now examples are Kyber, dilithium, saver. It's not moving. Okay, so the thing is, what we have to do is for module space exploration. So why it is important? Let's see. So here is a matrix. Now you have to do this polynomial multiplication. So you can put, let's say, n processors here, L square processors. Since all of these multiplications are independent, you can instantiate many such parallel multipliers Of course, it is very good for very high performance devices. So the latency is very low, but it also requires lots of area, power, area, energy, right? Now another scenario is you do not keep so much multipliers, but only one multiplier. The thing is, it is very slow. The latency is very high, but also the power consumption is also very low. So using module lattices, you can move to very high power or very low power designs. It is not possible with ring LWE or the standard lattices. Now, so this is one scenario which is very useful. So this is a very simple generic architecture of an IoT gateway. Since probably you know that IoT devices usually do not connect to the public internet directly. They used to go through a gateway server. So gateway server is quite large. It is stored. It is powered with very high power electricity lines and everything. So here we and also remember that these gateway servers, I mean, these IoT devices may be in one day or 1 week or in 1 month may connect to the gateway servers just to send their data. But these gateway servers, they serve lots of these IoT devices at a time. So for our gateway server, the throughput is much more important. But for these IoT devices, low power and low energy is very important. So what we can do, so using the same one single algorithm, one single scheme, model lattices, you can instantiate on the left side as a very low power implementation. But on the right hand side, because these are very powerful devices, you need high throughput. You can instantiate a L square multiplier, and instantly you have a very high throughput device. So with module space exploration, we can do this. Now the problem is, so see, I mean, I told you that even in the lowest case where you have only one multiplier, for Kyber, dilithium, saber, you must have a 256 cross 256 multiplier. You cannot go beyond that. This is the limit. So see, this is the now. See, this is the some recent results. So this is our work. So you see, these chips are not low power. So this is 140 milliwatt, and usually for IoT devices we consider around 1 to 10 milliwatt. And these are results are not even considering this KCHAC code. So even if you put the KCHAC code here, the problem is that these are not at all suitable for these IoT devices, right? And also the area is quite high. I mean, you cannot put them in IoT device or small devices. So yes, so even for the standards, there's one single multiplier is very expensive for small devices. So we have to explore other module lattices with different combinations of n prime and L. So what do I mean by that? So as I told you that since if n prime and L, if their multiplication is constant, the security stays same. So we can vary n prime and L, but we can still keep the same security. So this is a module space. So let's, in the standard lattice, what I told you, standard lattice, each number you can consider as a polynomial of degree 1. So in standard lattice, n prime is equal to 1 and L is equal to 768. Example is Frodo. On the other on the other end of the spectrum, you have fully one polynomial where n prime is 768 and L is equal to 1, which is called ring and ideal lattices. So examples are New Hope, Lizard. In the middle, you have some combination where n prime is 256 and L is equal to 3. For example, dilithium, saver, everything. But this is the module space. But what about others, right? We can have many more such combinations. So for example, think about this. If we go for something like n prime is equal to 64, I'm talking about this one multiplier. One multiplier becomes already very small. So think about this IoT scenario I told you. You can have a very teeny tiny multiplier inside the IoT, which is very low power and still give the same security as your standards. So we have to do for lightweight one solution is to do this module space exploration. Okay. Now, this is the war of our random numbers. So when we design schemes as a cryptographers, probably know, we often assume that random numbers comes almost for free. We focus on much more, think about your ECDC algorithms, your RSA algorithms. How many times have you thought where this random number comes from? For them, it's fine because there we do not need so much random numbers, right? So we assume that they come from for free, and we just focus on improving this point multiplication, polynomial multiplication, or scalar multiplication. Unfortunately, uh, in normal lattice-based systems, even the standards, we use SEC 128 or SHA-3 as a random number generator.
So this is usually how it is generated. So this is a large matrix where each of them can be a polynomial. We start with a random seed, we put it into shake 1 to 8, and you see we need lots of random numbers, 3.8 kilobytes of random numbers. It's already huge. And we have worked to improve in the main operation, which is polynomial multiplication. Unfortunately, we have improved it so much, the polynomial multiplication. Now, the random number generation, which is kind of an auxiliary component, it takes around 70% of the time in some cases, and 50% of area. So it already is very huge. Okay. But fortunately, we have something, it's called ASCON. ASCON is also a NIST standard, which is a very lightweight design. So one possible solution is it to remove the SHA, use the ASCON. Okay, so we have done some work in this case. So recently we designed this schemes called Rudraksh. So it's a kind of very Kyber-esque design. I mean, very similar to Kyber, but we did this module space exploration, and we found that for n time is equal to 64, it gives almost the same security. We also used ASCON as a random number generator, and it's actually because the initial results show that it is ultra lightweight design. So it is available online. The very good thing is it is 3 times smaller than the state of the art smallest design of Kyber. So we are doing ASIC fabrication. So also the similar thing we did earlier is called Espada, which is based on again same ideas, but it's based more much more based on module learning with error rounding, not errors. So I just want to mention that this Espada, that scheme we designed, this module space exploration, I told you about this Korean PQC, and there's a scheme called SMOG. So basically, this Espada is, I mean, SMOG is heavily inspired by Espada, and it is now a second round candidate in KPQC. Okay, so now more deployment issues. So the large signature issues. So PQC is very large. So this, think about this. These are the ECDS signature size, which is in couple of bytes, or maybe a few hundred bytes. Now this is the size of dilithium. This is a huge size. Almost in the lowest setting, you get only 2.5 kilobytes of signatures. So, and this incurs a lot of overhead in time and space for for TLS. That's why people are coming with new revolutionary ideas like CHEM TLS. We do not use the certificates at all. We do everything using CHEM because of these things. Think about it in a CA setting where you have this root certificate, lots of intermediate certificates, and then the end certificate. How big will be your signature if all of them becomes 3.3 kilobyte? The thing about this transmission overhead, think about this computation overhead is huge, right? And this is the reason. I mean, there are many problems. I mean, I have seen papers. People are working to remove these problems for these different protocols. And for the same reason, the NIST has initiated a new call where they have particularly focused that we have to design new signatures with smaller signature and very fast verification time, which unfortunately none of our current standards satisfy. Clear? Then migration issues. How do we migration? How do we do migrate to PQC? All of our infrastructure is based on classical. So there are many legacy systems where you cannot put PQC anymore. There are different organizations. They are not maybe they adapt to new schemes and different pace. Also, it's already. I mean, there are many IoT devices which you cannot just collect and put a new device and redeploy. So the only solution at this moment is designing hybrid schemes. So one example is okay. So hybrid scheme basically works with both classical and PQC, but it's not just simply you just merge together and everything will work. I mean, there will be many attacks. So I have given one very simple hybrid signature setting. So what you do in this case, you just do a first signature using this classical PQC, and then you do another signature with the message and the classical signature, and then sign this with the post quantum. Then the final signature becomes a concatenation of those two signatures. Now, if someone doesn't support PQC, they will only verify this first signature. If someone supports, they will verify both of these signatures. Although thorough security analysis is this is still a burgeoning field, it's in the very nascent stage, but a thorough analysis is required. Okay, now agility issues. What is agility? So this is our public key. Let's say we have designed a crypto processor. So I just told about the hybrid system. So this crypto processor must also work this with the classical cryptography, the standard PQC schemes, and then strong backup schemes. Why do I mean this? So because breakthroughs always happen in cryptanalysis. If you think about the lattices, right, the RLW or LW problem, these are barely 20 years old. I mean, in cryptographical terms, they are quite immature. So, for example, these were two very popular schemes, Rainbow and SIDH, and they were broken completely. They were the finalists. So, after 2-3 rounds of the evaluation, they become finalists, and then they got broken. So it might quite happen that there is a breakthrough in cryptanalysis of lattice schemes, and our current standard schemes, their security is reduced. So in this case, what we have to do, we have to keep some backup schemes. So NIST also mentioned that this is important, and that's why they have put Sphinx and McElis also as a backup schemes, because these Sphinx and McElis are 50, 60 years old schemes, and we are very confident about their security. So this agile crypto processor, we have to put new crypto processors which are very agile, which can not only do delirium, Kyber, but many things. Okay, yeah. So just this hybrid processor, and then of course this physical attacks and countermeasures. So this is one of the most potent threat for deploying this any cryptographic schemes. Now, your scheme can be very secure mathematically, but unfortunately, when you run it on a processor or your microcontrollers or wherever, it is possible that I do something on this. These things leak a lot of information about your secrets. So this can be passive attacks like power side channel timing, electromagnetic radiation, or it can be active attacks like voltage glitch, row hammer attacks, cache attacks, electromagnetic attacks, etc. Okay, so we did one work. So this is based on because we attack this core component of any lattice-based scheme. So this every lattice-based schemes, they use polynomial multiplication. So we did this correlation power analysis attack, and we exploited this narrow distribution of secret values. And our attack worked on 3 out of 4 finalist schemes. That means Kyber, Saber, and N-True, and it worked on all of these different multiplication methods, and we were able to recover this all the secret values. So this is a published work. So we were able to recover all the secret keys in within an hour in the online phase. Okay, so protection schemes, of course, we have to work on lots of masking schemes. So how the masking schemes work. So you have this input and output. This is your secret. If I do side chaining attack, I get information about S. In masking, you split the secret in 2 parts and then repeat the same operations, and then somehow at the end you combine. Now the goal is that even if an attacker is watching one part of this algorithm, he or she doesn't know the other part. So your secret stays safe. So these are the basic concept of masking schemes. But the problem is that masking, although provides this proven security, see, there are some state-of-the-art implementations. You see, for the third of masking, the Kyber's overhead is almost 30 times. So it's huge, huge overhead, right? Although it's secure. So now think about these IoT devices. They are not even applicable for IoT devices. That's why we have to find some new methods like shuffling, chip level countermeasures for IoT devices or low power devices, right? Okay. So then we took it one step forward. I mean, there's a new type of attack comes in. It's called cross attack. So why this is important? I told you about this side channel attack protection in masking, right? You have developed lots of good masking schemes, and now you have put it into public level. Now you cannot restrict the attacker. They see, this is my side channel protected scheme. You cannot do any other attack on this. Attacker is free to choose any type of attack. Your scheme may be side channel protected, but I can do fault attacks on that. So this is the idea of this work. So this was a masked implementation. SC attack is not possible. It was proven. But then we saw that we can do, because to put this masking, you have to introduce many new components. And we can actually put faults there, and it gives us a much more advantage than normal fault attacks. So this is again a published work. It is one of the top flagship conference for this type of work. Okay, then I think I'm running out of time, so I'll quickly finish. Then the problem of indigenization. So this is a very basic very basic life cycle of a cryptography scheme. We start with hard mathematical problems, then we design, we propose parameters, then we do proof of concept implementations, we do physical attack, then we do some optimized implementations, we put it into protocols because these are primitives, and then we deploy in the real world. So for indigenous design, we have to do, so we shouldn't really outsource any of these parts to, at least for the national security or for very critical components, we shouldn't give it to third parties. The thing is that, see, I mean, we didn't have any standard documents, standardization. It's fine. We do, but after this, let's say we have designed and did everything till here, but we then gave to synthesize our chip to some company. The thing is, it is very easy to put some backdoors there, and then everything is, there is no point in doing everything because your scheme is ultimately weak. So this is the point of we have to focus on covering all these parts indigenously. Since only we can move into a proper PQC, quantum secure world. Now the good thing is right now our group and there are many other groups, few other groups in India which with combined expertise we can almost cover the entire spectrum. So I have just given some of my works. So we have designed lots of schemes, which are some of them are state of the art. So this saber, which was one of the part of the finalist, then this Rudraksh, which is a lightweight design. This PQ signature Vidu we have designed based on multivariate. Right now it has the lowest signature of only 96 bytes among all the post-quantum signatures. Then we did lots of software implementations, many fault attacks and side channel attacks. Some microarchitectural attacks. This is one of the first of its kind into doing row hammer attacks on Kyber. Also, we did lots of countermeasures for all those attacks, and then of course, then we did some ASIC implementations, which is, as I showed you in one of my earlier slide, that one of the lowest power and lowest area design of PQC currently in the market. Okay, so I'm done. I will be happy to answer your questions.
Would talk in a very short span and a lot of work.
Yes.
The balance between lightweight to all the heavyweight,
Yes.
which you showed, is it a matter of choice of this, at least for
Sorry, I'm not. Yeah, please.
Is it a matter of choice between the three parameters, ring size, the model, let's call it the finite field size, and the module metric size?
Exactly.
Is it the question of that? In which case, my just last question: have people studied the variation of this with the lattice hard problems, their dimensions, and so on?
Exactly. So that's a very good question. Thank you for asking this. So yes, first of all, of course, it is kind of, I would like to call it as an optimization problem, right? You can, so for example, I can give you, so you can reduce the queue. The problem is that if you reduce the queue, then it becomes very prone to failures because lattices are not 100%. These are actually error-prone solutions. We want to keep this less than 2 to the power minus 128, the failure probability. It is not like 100% perfect solutions like RSA or Diffie-Hellman, right? So it is kind of an optimization problem. We have to choose many different parameters and then, tweak something here and tweak something here. Basically, a search problem. So, I really cannot, I'll be happy if you can read the paper and let me know. So there are many things we have to optimize. It's a multidimensional optimization problem, I would like to say. So then we did a huge level of search. It's not like just I run a Python program and I'll give, it give me the parameters. So we have to do lots of changes in between and then see how the results come up. And then we got a satisfactory result and then we put it in. Your second question is, see, these are all modules. So the good thing about modules is modules give a very uniform view of these whole lattices. The spectrum I showed you, see the standard lattice and ring LW lattice, all can be thought of as a different dimensions of lattice. So as long as we stay in the module space, there is reduction from ring SIS to module SIS. So as long as you stay in this module space, we are fine with this security problems. So does this answer your question or?
That's okay. Just an extension, small. That's fine. Module space. Now, in general, learning with errors, this even some kinds of a code error decoding problems, and then the lattice problems, they're all similar. Okay.
Exactly.
So it's worthwhile probably to invest A lot of
Exactly. No, in the paper we have did a thorough evaluation of everything. So all the different types of attacks have been considered, and then we designed we proposed the parameters. Of course, I know this must be done. Yes, we have done it. Thanks. Thank you for the question. Yes.
Sir, can you tell us like how difficult it is to do side channel analysis on the quantum algorithms?
Well, this is very much from our perspective. Uh, as I told you, this fault attack on side channel, it was very, complex attack. So we had help from Professor Devdeep Mukhopadhyay SEAL lab. There are like the CPI attack. This was, I would say, a bit easier than this attack. So it all depends on what type of adversary you are assuming, uh, what is your setup and everything. So unfortunately, I cannot comment on how easy it is to do attack, right? Yes.
No standard formulation has been done.
No,
So
no.
we have to identify which module has to have more possibility of finding the side channel attack, right? So then how do you execute that side channel attack process in your
So I don't know. How do we execute? I mean, so we.
every module has some specification, right? So you have to focus on the module where the side channel attacks are possible.
Okay.
So how did you define? Because as of now in this, the standardized has come out, but verification has not come out.
So NIST doesn't standardize any fault attacks. Okay, it will only or any type of attack. It will only standardize the scheme. So think about that's AES, right? People are still finding new dimensions, new type of attacks on AES. So this still keeps progressing. So when we do, we see that okay, what are the existing attacks, and if we can improve this, if we can change this parameter, you can change this setting, you can if we can improve these attacks further.
Keep improvising the schemes. That's a good design. So when I
No, okay, I said improving these new attacks. I mean, you cannot say that after this time there will be no different fault attack or side channel attacks possible on these schemes. So as I gave you this example, people are still finding AES was how much 25 years back. Still, there are new attacks on AES, right? So,
but comparing to this post quantum algorithm, because as compared to many of the uh, checkpoints, what the NIST has been done, still the fault attacks, the side channel attacks, the possibility as well as you have been coming out with your lightweight cryptography, Rudraksh, for the replacement of Kyber.
okay.
So in that possibility, you have overcome that side channel attack.
Exactly. So while designing, because we have designed this after, NIST is proposing new standards. So we have already in the paper we have mentioned that how it can be. So we all there's a concept we call it's called masking friendly designs, or so we already have put some designs strategies here, which will make it little less prone to fault or side channel attacks. Also, these masking schemes and any other countermeasures you are developing for Kyber, those can be applied to our designs also. Because see, I mean, I'm talking about module space, right? So I mean, we are just reducing the polynomials and increasing the matrix size. So those countermeasures which you are applying for Kyber, it can also be applied for our schemes. Also, the schemes which the attacks which are applicable to Kyber is also can be applied to our schemes. So
whether your scheme overcome that, the drawbacks of the Kyber.
So we can only make it less prone to attack, but nobody can say that our scheme from design is prone to these attacks. It's not possible. Yes.
So while optimizing the parameters or dimensions, how we will ensure that this will remain FIPS or some recent?
Okay, so this will not go into FIPS, but I would also like to say that please, I have encountered this question many times. FIPS doesn't mean the end of innovation in the field of lattice-based cryptography. As an example, there was FIPS 203 for elliptic curves, right? After that, there were 5 more standards. Right.
Yeah.
Fine. So it is not like that since a FIPS has published, we should stop now. We should keep innovating. And there is actually a lot of buzz in designing lightweight for post-quantum cryptography because, as I told you, NIST itself has initiated a new scheme, new process to standardize more signature schemes. So it is not like that FIPS 203, 204, and 205 have been developed. We should stop here. No, and there are. So this KPQC schemes, if you see the KPQC schemes, there are more designs coming up, and even in the print, lots of new designs coming up. So in 1 week, I have seen a very efficient intro-based design in print. So, yes.
But at the same time, this is that if it is not standardized, it means it is not secure actually. This is what, or there is no security actually.
No,
There is statement actually.
so this is in the design. I wrote one word that I love to call it. It's called Kyber-esque designs. So Kyber-like design, right? So we have taken into, we can show that if our scheme is vulnerable, Kyber can be also vulnerable. So our scheme is almost at same level as security as Kyber. So now if you are a designer, if you are a new, let's say you are implementing, you want to do IoT implementation of Kyber, you cannot do it. I just showed you. Then you have the option to do these things. Right, and there will be maybe. So we had AES, but we still did lightweight standardization with ASCON. So it is a possibility that in the future there will be a lightweight PQC competition, and there we will submit. So once NIST announces new standardization protocol, you cannot start working then and submit something, right? You have to be prepared from much before. So I can see it that way. Okay. Yes.
So I have one question. That is, first of all, thank you, Angshuman, for this nice talk. So when you talk about like lightweight PQC, right?
Exactly.
So you have also considered, I believe, like other problems like LWR based and also
Exactly.
code based, right?
Exactly.
So do you think that like there is an opportunity to look into those hard problems in the context of like getting maybe designs which are based on 0 and 1 or binary
Exactly.
decompositions?
That's a very good question. Yes, exactly. So we are looking it into different different lattice combinations and also other schemes. So the one I think it was in the design is called VDO. VDO is a multivariate based design, and it has only 96 bytes of signature, which is smallest as far as I know. Right. So why I showed you this Rudolph design, because this is very much similar to Kyber, and just as I discussed that it is much more easy to argue that still it is secure. So yes, we definitely has to look for. So I just want to again tell that even in this new call for signatures, they have specifically mentioned that they do not want any lattice-based designs. They will focus on other designs more. So of course, this is we have to look into others, and I personally feel that because of this so much popularity of LWE, the other designs, this code-based, multivariate-based, and these things are quite neglected. So it is the right time to look into those things.
Yeah, when you look at LWE, right? I mean, usually there is an error involved, right? But when you look at the counterpart like LWR,
Exactly.
right, it is more deterministic. Right?
Exactly.
So that is an interesting, like choice in the context of things like fault and things.
Exactly. So we already designed one LWR with integral 64, which I told you. So this is actually this was acknowledged by the designers. This is very much influenced the SMOG scheme, which is currently in the second round of Korean PQC. So yeah, we already have done some work there. Yeah, that's a good. Of course, this is LWR is already always very attractive scheme to design. There, it has much more. So apart from LWE, it is very, very, very friendly for masking designs. Okay, more questions. Okay, thank you, everyone.